the day before the panel. Sergio could not come today. He had a medical issue, so he sent us a video, and we will upload it on YouTube and send you all the link. We were running behind considerably, so we're trying to see if we can get caught up a little bit. So our next talk...
I'd rather listen to Sergio than me, so we can swap them.
So the title of the next talk is Energy Efficient MIMO Precoding is by Lee Swindlehurst, who is a presidential chair at UC Irvine. He's an IEEE fellow. His expertise is in detection and estimation, signal processing for communications, MIMO, sensors. So I'll turn it to you.
Thank you, Andreas.
Thank you.
Thank you, Yorgos, for the invitation and for organizing this event. As I look out on this group of august individuals, people who I've looked up to for many years and gotten to know and worked with, the only thing I could think of was just imagine if a meteor were to hit this building. The loss of the experience and talent here would be an immense devastation to our community. So anyway, this is the idea. You know, if you have so many people gathered in one spot, it's not a very robust solution. We should be more distributed. Anyway, thank you for the invitation. I'm very happy to be here. Of course, always an admirer of Yorgos and his work, and it's an honor to be selected to join this group. So I also changed my title a little bit. You know how it is, but I will talk about precoding. Yorgos and I overlapped on MIMO and precoding. Quantization also I'll talk about today. I should acknowledge my co-conspirator, Van Lee Nguyen, who's my former PhD student, currently my postdoc, and some other collaborators that I've had over the years. Let me begin, though, with giving you the law of Giannakis, or Giannakis' law, that I've come to learn over the years, and that is the probability that you will see Yorgos, given that the conference you're attending is in a very nice tropical location, asymptotically approaches 1. And in fact, Yoram mentioned today he didn't have a photo with him and Yorgos together. So I've added one with Yoram and myself. This was just recently in December in Costa Rica, a tropical location, so Yorgos was there. But I think all the photos I have with Yorgos are in locations like this. Puerto Vallarta, you know, Aruba, you name it, he was there. Of course, I was there too, so.
I think I saw.
Yeah, that's right. All right, so energy efficiency is a very broad term. I'm going to talk about it in relation to massive MIMO. There have been, I guess, there are many different approaches that you can think about using when you talk about energy efficiency with massive MIMO, large arrays. Massive MIMO, of course, a few years ago meant, you know, like Robert was talking about, and Paul Raj, you know, 30, 40, 60 antennas. Nowadays, people are talking about thousands of antennas. So, you know, what's worth doing is worth overdoing in the community. And so Robert talked about one of the two general approaches, and that's using analog type preprocessing together with digital processing in an attempt to try and minimize the complexity, energy consumption, and cost of building these large array systems. I'm going to talk about the other approach, to keep everything digital, right? We love digital. Digital gives us a lot of flexibility. It has advantages, has its disadvantages we'll talk about as well. So I'm going to talk about using digital hardware for massive MIMO systems, but instead of using high fidelity hardware and, you know, being bound by those constraints in terms of complexity and cost and so forth, using cheap hardware. So build lots of things that are really cheap rather than fewer things that are real expensive and high fidelity. And it turns out in many ways, building lots of things that are cheap, just having a whole huge number of them, in many ways is better than having fewer things that are high fidelity. You can gain more in one dimension than you lose in the other. So that's really the message I want to talk about today. So let's see. Oh, by the way, I always use this slide, and I don't know if Robert's still here, but this figure here is from Robert. I've been using this for about 10 years. This is the 4G version of the slide. You saw Robert's slides a moment ago. He's using the 5G version of the slides. But this is just a picture to illustrate, the hybrid analog digital solution where you have some kind of RF combining network that precedes the digital RF chains. This has probably received the most attention in the literature and also in industry. People are starting to construct systems like this, beam searching systems. Reduced dimensionality with this beamforming network. It does have drawbacks. Robert alluded to some of these. It obviously complicates the receiver design because you have to design these somewhat separately. You lose some flexibility. There's scalability when you go to a very wideband system. So anyway, at least there are enough reasons to consider alternatives, which I'm doing today, and that's to use a fully digital system, but with, on the receive side, low-resolution ADCs, and on the transmit side, when we talk about precoding, you might say low-resolution DACs, but I will argue that there's maybe a better approach to use than that. So let's go on. I don't want to spend too much time with the background. So it works. I mean, this is a simple example with, if you have enough antennas, basically, with only one bit of quantization at the receiver, you can get 16 QAM for 9 users in this example. You can get more if you want. So some people say, well, with 1 bit, how could you even receive something more than QPSK? But with enough antennas, you can do pretty nice things. This is a case where you can get 16 QAM with 1 bit of resolution in each antenna. If you do something clever, because your users have spatial correlation, maybe they're located in some sector, 50 to 60 degrees sector, you can do something called sigma delta sampling in space, not sigma delta in time, sigma delta in space, and you can take advantage of that spatial correlation and do even better. So here we're getting 16 QAM, same scenario, 400 antennas. And you can even go as, this is 64 QAM. You can actually do 64 QAM with a single bit of resolution at each antenna with a little bit of extra processing at adjacent antennas to do the sigma delta processing. So, it is amazing that you can actually recover, with enough antennas, you can recover relatively high fidelity signals with just 1 bit of quantization at each antenna. So we did it this is a few years ago, together with Joseph Nozick at Munich, where I spent some time. We did a fairly detailed analysis of the comparison of energy and spectral efficiency between these hybrid analog digital approaches and fully digital but low resolution approaches. And the results were published in this paper. We tried to take into account a relatively accurate energy model for the electronic circuits in the RF domain. And we came up with this result here. There's a lot of things pictured here. Basically what it says is that at lower SNR here on the top, the red curve corresponds to a fully digital system with low resolution receivers. And it's a plot of spectral efficiency and energy efficiency together for different bit resolutions. Every point on these curves corresponds to a different bit resolution for the receivers. So you can see in the case of low SNR, very low SNR, 1 or 2 bits at the receiver is good enough. So in low SNR, the key problem is not the quantization error anymore, it's the noise. As you go up in power, still here we see that 1 bit is winning out. The rest of these curves over here are different flavors of hybrid analog beamforming. When you go up in SNR, you still benefit from the low resolution approach, but you need maybe 3 or 4 bits of resolution to really get the best trade-off between spectral and energy efficiency. And then as you go up in SNR, the number of bits stays about the same, 4 or 5 bits, but you can see you start to lose the advantage, and the hybrid approaches begin to have essentially the same trade-off in terms of spectral and energy efficiency. So there is a place for these low resolution architectures, and they tend to be in situations where you're low power, you're SNR deprived. And in those areas, they offer a very good alternative in terms of spectral and energy efficiency trade-off. And in fact, we can do much better. This was just using a very simple receiver, just a simple least squares channel estimator with some 5G NR pilots. We can do much better than that, and that's one of the things I wanted to talk about today. This is the work of my postdoc, Ben Lee. So the problem with, so 1-bit, why there are so many papers about 1-bit receivers, and it's not so much because that's the best choice, but that's the easiest one to analyze. It's the easiest one to mathematically formulate problems for and analyze. The problem with analyzing higher order quantization systems is just that it becomes a little bit intractable mathematically. But with the help of some deep unfolding techniques, we can get a better performance. So I'm just going to show here, this is just a standard uniform b-bit quantizer with 2 to the b minus 1 thresholds, 2 to the b threshold levels or quantization levels. So just for this, what I'm going to talk about is specifically for the case of a uniform b-bit quantizer. And so we're going to consider the standard problem where you have a training phase, we quantize the data, you try and estimate the channel, and then once you have the estimated channel, you're going to do maximum likelihood data detection during the data transmission phase. Again, the data is quantized in both phases. And so the idea is you transmit a pilot matrix during the training phase, you estimate the channel with the 1-bit observations. Again, you're going to use a maximum likelihood channel estimator. You're going to then use that estimate of the channel to detect the data and decode the transmitted symbols. And then you could, of course, repeat this process, use those decoded symbols if you wanted to update your channel estimate, but we won't go into that detail here. So what I'm going to talk about the approach we use for data detection here. It's actually the same approach that we use for channel estimation because, you can see the model. Whoops, that's not what I want to do. If you're estimating the channel with a known waveform, it becomes, this equation is linear with noise. But it's the same problem if you know the channel, you're trying to estimate the data. The only difference is the data is, from a constellation, so you have to do something a little bit different. But essentially, whether you're estimating H or whether you're estimating X, where the other term is known, it's the same. It's basically the same problem. So I'll talk about the data detection problem here, but exactly the same approach applies for the channel estimation problem. So if you want to do a maximum likelihood data detector, of course you have to know the likelihood function. And so for a uniform b-bit quantizer with quantization levels here, measurement observation y here, it's pretty straightforward to derive the expression for the log likelihood function. It's going to be the log of the difference of two CDFs, for the, assuming that the noise is Gaussian. Two CDFs, one at the upper transition point and one at the lower transition. So in other words, the probability that y is here is the probability that's below this point and above this point in the quantization table. So you get this formula here. This function here is highly nonlinear. If you were going to try and optimize this, it's a fairly intractable problem. And so you might, not only from the point of view of having to deal with the fact that X is from a fixed constellation, so it's an integer optimization problem. On top of that, of course, you have the fact that it's just a complicated problem. Not convex, right? So obviously. So you might say, well, how would you try and optimize this? Well, you might try a gradient descent approach. You might, pick a value of X and then take a step in the negative gradient and see where you end up. And so you could try that. So here's again the log likelihood. Here's our maximum likelihood estimate. The problem is that we're at the tail end of these CDF functions. And so if you try and compute the gradient and you actually try and implement some kind of gradient search to solve for this MIMO, this finite alphabet transmit signal, you end up with big numerical problems at high SNRs. And actually moderate SNRs, I should say here. So what you can do instead is replace the the Gaussian CDF with an approximation, a logistic approximation. A sigmoid function, I guess, is another term for this. This is a standard approximation for the Gaussian CDF function. Turn this problem into this one. And it turns out if you make this one little change, suddenly the gradient, even though it's an approximation, the gradient becomes much, much more robust. And things suddenly work very well. And in fact, what you can do is then, instead of implementing the gradient search as you normally would, just by implementing a search with a certain step size until you find a local minimum, you can do what's called deep unfolding. You can create an unfolded network, a neural network, where each step of the iteration becomes a different layer of the network, of the neural network. So here, for example, if you're doing a projected gradient descent, projected because, of course, x is from this finite constellation, this would be the standard gradient update step. So instead of implementing this as you would in a standard gradient descent, let's implement it with a network here. Implement these steps with a network. Replace the gradient here with this sigmoid approximation. Sigmoid functions are often used in neural networks anyway, so it kind of fits well with this kind of architecture. So you can see the sigmoid functions are here. And so you take your estimate at one layer of the transmitted symbols, you pass it through this projected gradient update, and you get the next set of estimates. But the key to this working well is you make these various parameters here, the step size, for example, and so forth, the parameters, also the parameters of the projection function. You make these parameters tunable. And so you train those parameters in your network and then implement this unfolded, it doesn't have to even be deep, unfolded optimization. And the performance is remarkably robust. And that's what I'll show you here. So this is a plot of bit error rate versus signal noise ratio for 1-bit and 2-bit receiver. There's lots of plots up here, but the top set of curves in both of these cases are receivers that we developed that were based on basically linear receivers for the MIMO problem. And you can see there's a large gain that you can get if you go to the maximum likelihood approach and use this unfolding technique to implement it with the trainable parameters. You can get a very large gain and down into the region where even just with 1 or 2 bits, you can get the network to perform very, very well. And then if you want, I don't have any time to talk about this, but if you want, you can even go farther, and instead of doing a maximum likelihood detection of the data, you can actually try and implement something that approximates a minimum mean squared error data estimate. That's intractable if you want to do that using the standard expected value of x given h approach. But if you use variational Bayes techniques and come up with approximations for these posterior probabilities, you can actually even get bigger gains. So the technique I just showed you a moment ago was the blue square, the unfolded network. If you use this technique based on variational Bayes, you can get down now to this red dash curve. And this one here is the case where you have perfect CSI with perfect quantization. So with this is with, again, I think only 2 bits. You're very, very close to the limit in terms of performance. So I guess, part of my message today is that, we think there's still some good things that can be done with systems, especially systems that have very, very stringent size, weight, and power constraints, to considering all digital approaches with these low-resolution receivers. So I promised to talk about precoding, so I'll talk a little bit about precoding as well. So here's a picture of a conventional linear MIMO transmit precoder, where we have data that comes in. It's coded and then precoded for a spatial processing with some precoding matrix P. This could be a zero forcing beamformer, a minimum mean squared error beamformer, some kind of beamforming. Goes through a DAC, low-pass filter. It's modulated to the carrier frequency and then spit out the power amplifier. And if everything works here, it's some scaled version of the digital signal here. And the linear precoder, the purpose of the linear precoder is to try and pre-equalize the channel and eliminate the multi-user interference. But even if your data that you're trying to transmit is constant modulus, the precoded signal will not be in general. And so you have to operate your power amplifier with some backoff to avoid distortion. And then, of course, DACs are not particularly low power devices, but the backoff is the big problem here in a conventional implementation. I want to show you a different type of architecture that has been proposed recently that fits in well with the idea of nonlinear precoding, which I've been interested in for many years, techniques that encode the data that you want to transmit or precode the data in a nonlinear fashion. And there are huge gains that can be obtained if you allow yourself to use a nonlinear precoder. Of course, this requires a precoding that happens on a symbol level. So it's a very fast rate precoding. It's expensive computationally, but there are big benefits. And so the precoder here in this approach is actually a nonlinear precoding, a nonlinear mapping from the data to the transmit signal. And the precoded signal is in fact, because it's in effect up to you how you choose this, you can choose this signal here to be, in a sense, already matched to whatever bits of resolution that you have. So in other words, if you have 2 bits of resolution, you just guarantee that this signal is QPSK. If you only have 4 bits of resolution, you guarantee that the signal is 16 QAM. So by design, since you know, you don't have to worry about quantization noise in this case because you control the signal itself. You can eliminate quantization noise. So there's no DAC here, but you make the precoding low resolution in the sense that you constrain the set of signals that you transmit from each antenna. And in fact, you can constrain the signal to have a very low PAPR, and hence you can avoid the backoff. How would you design such a precoder? Well, this is a paper that was just published last year by a colleague of mine at UCI, Payam Haidari. And he's been designing, this is the result of several years of work, designing a direct digital modulator for RF systems. And this is exactly the idea that I was just talking about. Your precoded signal is basically built up by a set of QPSK waveforms they're power combined prior to being transmitted. So the actual signal that is being transmitted is a QAM signal. There's no DAC here. The data have just been somehow mapped. The data you want to transmit have been mapped from the data domain into this precoded signal with QAM transmissions from every antenna. And there's a huge there's several advantages for this technique I'll point out here. So again, it's very essentially insensitive to a PA nonlinearity. So this is a single carrier system. I realize that all systems are OFDM and so this is research, but that's why we study it. Insensitive to PA nonlinearity because you essentially control the PAPR. You can reduce the backoff. You don't need a DAC. This particular approach is shown to have better noise performance and much, much lower power. So the power consumption for a conventional receiver, this is again using a fairly sophisticated analysis, about 2.5 watts per channel. This particular implementation is down below half a watt on the transmit side, which is a good savings. Of course, this is a more complicated power combining that occurs here than in most in the conventional system, which is just you're combining the I and Q parts together. Here you're potentially combining a larger number of signals here, depending on the dimension of the signal you want to send, and you have a little more complicated LO distribution, so you don't get anything for free, of course. But this technique exactly matches this idea of using nonlinear precoding. Because you take the data you want to transmit and you map it somehow onto the bits that you're actually transmitting from the antennas. And so there are several ways to do this nonlinear precoding. This RF QAM, he calls it the RF QAM architecture, direct digital modulation. One approach would be to design your transmit signal at any given time such that once it passes through the channel, you end up with at least something close to what you want to receive at the receiver, possibly with a scaling under a power constraint. And this is an ML decoding problem, but on the precoding side. This is an ML precoding problem, but it can be solved just like an ML decoding problem, either with the techniques we were just talking about, using unfolding, using sphere decoding or sphere precoding in this case. Or another technique that we've been working on is to use the idea of constructive interference, interference, where you don't try and map the received data directly on the symbols. What you do is you just basically try and map them anywhere in the region where they would be decoded correctly. So Z is the noise-free received signal. As long as you guarantee that the noise-free received signal at a given user is in this region with some safety margin, then you know the receiver is going to decode that symbol correctly. And that gives you more flexibility to either become more robust or reduce power. And again, this is actually a convex problem and can be solved in a fairly straightforward way. And this is the kind of result you might get for this kind of receiver. So this is at the receiver. So here you're transmitting 16 QAM data to users, but you're only using QPSK transmissions from each antenna. So the data is 16 QAM, but you map it into a large array where each element is transmitting QPSK data, and you do the mapping in such a way that when the receiver gets the signal, they will see the right 16 QAM signal that you started with. So orange here represents if you do a zero forcing solution. So of course all the received signals are clustered around the constellation points. But if you do this, for example, the safety margin precoding, you notice that some of the points are out in this region here and out in the corners away from the decision boundaries. And so they're much more robust to noise than, say, these sample series. You get a much better and more reliable transmission by exploiting a nonlinear precoder here, which essentially just pushes the received signals away from the decision boundaries and makes the system more robust to noise. And another thing you can do is actually, by taking advantage of this safety margin approach, you can actually, in fact, transmit data to more users than there are antennas. So here's a plot of a case where you have 9 users, 13 users, 17 users, 8 antennas, 12, 16 antennas. So one more user than there are transmit antennas. And you can get a throughput that's much larger than you would in a standard conventional system, in this case using regularized zero forcing, which is a fairly robust scheme. So this is just a little, I guess, a plug for the idea of doing something a little bit more sophisticated than just linear precoding in MIMO systems, doing some nonlinear precoding. A few years before this, we were working on vector perturbation precoding, which was a little bit of a generalization of Tomlinson-Harashima precoding, if you're familiar with that. Again, it's a nonlinear precoding technique, a little bit complicated to implement, but it comes with some pretty significant gains in many cases. Anyway, that's it. That's the end of my talk. I'm just making a plug for low-resolution architectures as an alternative to the hybrid digital analog approach that's so prevalent today. Better energy spectral efficiency trade-off, I think, at the SNRs that are typical for massive MIMO systems, which tend to be lower SNRs. You can do fancy things like sigma delta in space if you really want to get high fidelity performance with very low numbers of bits. And then using deep unfolding techniques, this is I think a problem that's perfectly set up for deep unfolding solutions, and we've shown them to work quite well. Better gains even on the transmit side because of the reduced need for back off. Now the challenges are where, of course, we're trying to look at now. These are the areas where I think more research is needed. If you're in a high SNR region and you don't have non-Gaussian, if you're in a region where you're non-Gaussian, you have just a couple of users, for example, in a line of sight setting, so you don't have a Gaussian type of setting, you might have to use something like dithering to get good performance. This is a tricky problem. There are some in this audience, I know, like Robert, that have worked on this topic. This is also very interesting. You need uplink power control to make this work the best. So if you're using low resolution data converters, if you have any one user that's stronger than another, you'll get out of balance performance. This is the Achilles heel of low resolution processing is the power control problem, and which means basically if you have a strong jammer, you're also dead. But there are ways to get around this using sigma delta that we're working on that you can handle this in certain cases. And then out-of-band interference has to be controlled, but there are some pretty standard ways to handle that. So these are the things that are, I think, holding back, I think, more a stronger adoption of these ideas. But I think to some extent they can be reduced. And the gains are fairly, I think, can be quite important. So that's all.
Questions from you? One, has somebody looked at the issue of DC offset for 1 bit?
Yes. So there are a couple of researchers that have looking at different quantization thresholds. John Lee at Florida has been one that's looked at that and studied that there are gains to be had by using some diversity in terms of where the 1 bit threshold is. Yes. Mm-hmm. The gains aren't huge. You get a couple of dB of gain though. Mm-hmm.
So this 4 prime becoming 16 prime, so it's kind of it's on the both sides of the beam. I wondered how the side look like.
Yeah, and that's the out of band, I guess, issue that. And that. So again, there have been some analyses of this, and I think my understanding, this is not something I've looked at in a great detail, but there have been ways to do some analog filtering to fix this problem.
Thank you very much. Very interesting talk. The safety margin recorder, is this implemented using a neural network? What are you using?
It's a convex problem, so you can solve it, but you have to solve it at the symbol rate. So it's a convex problem that has to be solved at the symbol rate. It doesn't require. So for the precoding part, no, it doesn't require a neural network solution, right? Yes, Brian.
So there's old results on 1 bit dithering, and then you oversample. Like if you want to estimate correlation, you could convert.
Yep.
Have you thought about oversampling? What should we do with that?
Yeah. So you could certainly do oversampling. We didn't think that was so exciting, so we thought about doing it in space rather than time. That was the sigma delta approaches that I'm talking about here are, in a sense, if you oversample in space is one way to do it because then you get spatially correlated signals that you can exploit with the sigma delta. But the way we've tried to sell it is that's maybe, in a sense you're getting just as much, you're getting more data. It's just a way of getting more data. We want to reduce the amount of data we get, so.
Yeah.
So
that question of the strong interference.
Yeah.
That's the killer, but if you dither and then sample faster, you're effectively getting more bits.
Right, yes.
Like I wonder what the energy trade-off for that would be.
And that's one of the things we're looking at. The other way you get high spatial correlation across your array without having to put the antennas closer together is to assume you're in a scenario, which is often the case in MIMO, where you have sectored users. Especially, for example, on a mask, you've got in the elevation dimension, you usually have a fairly sectored, really looking about minus 15 down to minus 40, 50 degrees in terms of where your users are. It's a very sectored set of area where your users are, and you can really exploit that to your advantage, even without putting your antennas closer together with this sigma delta idea. So we focused on doing it in space rather than time, again, just to reduce the amount of data that has to come from the radio head down to the ground. But you could certainly do it in time as well. Yes, Mikhail.
You discussed the comparison with the hybrid architecture
Yes.
in terms of complexity and so on. So that's
it wasn't, well, it was energy and spectral efficiency, right?
But I think Rob was talking about this earlier. Also discussed the dimension of the feedback that you need and the constrained feedback rate. Is this approach, could you, how does this compare? Could you mimic basically the beam space type of formulation that the hybrid system will give you.
In this analysis?
This general low quantization, many digital streams
Yes.
Implementation. How does it work when you have limitations in the amount of feedback of child state information that you can get?
Well, this, I think, the analysis that you're speaking of here that I showed you here was assuming a TDD type of setting, so we're not assuming feedback. So the idea of exploiting feedback to design, is your feedback quantized is one question, just like your data measurements are, and of course you would assume they are, unless it's some low rate channel. This is a problem that hasn't really been looked at much. If you're implementing a low resolution transceiver, but you have feedback from the users, quantized or not, how that impacts your choice of, for example, thresholds on the ADC, how you allocate the bits. This is something that hasn't been looked at. I think I have not really focused so much on the FDD case. I've been focusing more on TDD, so I haven't considered that, but I haven't seen much in the literature that has discussed that. So I think it's actually an interesting open problem.
Thank you very much.